So recall that our residuals were defined as E equal to y minus y hat, which we could write as I minus the hat matrix times y. And again, now we're in the context where we're going to assume y is normally distributed with mean x beta and variance sigma squared times I. So the residuals then are singularly normal distributed because this is not a full rank transformation. So the residuals are singularly normal distributed, and their mean expected value of the residuals is I minus h of x times x beta, which is 0, because, for the reasons that we've discussed at length. The variance of the residuals is then I minus h of x sigma squared I minus h of x, and then which is just I minus h of x sigma squared, since the matrix I minus h of x is idempotent. So the residuals have this issue, or not issue, but they have this property that they inherit the units of y. So of course that's a good thing. They're a linear transformation of y, but that often means that if we do things like a plot of our residuals, which we often plot, say for example our residuals versus our fitted values, it's a terrible y. The scale, the vertical scale, when we look at that, isn't comparable across experiments. And so if you wanted to standardize your residuals, that's some of the things that we're going to talk about in this lecture. So what you could do is simply take the diagonal of the variance of E, that matrix, to the 1/2 power. So what I mean by that, I'm not writing this out perfectly, but the square root of the diagonal of the variances. So let me write it out here, to the minus 1/2 power. So I just mean the diagonal matrix that has the rate, the inverse of the standard deviations. And if we were to multiply that times our E, then we would have now random variables that have a unit variance, though of course we'd have to estimate the sigma squared. So that is a nice way to do things. So, and of course it satisfies our criteria for creating a unit-free quantity. However, these quantities, these so-called standardized residuals, have the problem that you can't easily establish, I guess I should say, boundaries for calling standardized residuals outliers, just because the distribution of this quantity isn't a terribly easy distribution to work with. It's not a t-distribution because the numerator and the denominator are not independent in the same way that our typical t-statistics that we derive for, say, the coefficients are. So we're going to talk a little bit more about how to get more t-like residual statistics here when we talk more about different ways in which we can standardize our residuals. But this is by no means a terrible thing to do, to take our residuals, say EI, and then divide it by the, let's say, square root 1 minus HII, where HII and then times S, where HII is the ith diagonal element of the hat matrix. That's often a quite useful thing to do. Another just a little comment that we might need later on is, because the variance of E is equal to I minus h of x times sigma squared, we know that that has to be greater than or equal to 0. So we know that any element, any element of this, the diagonal of this matrix, has to be greater than or equal to 0. So 1 minus HII, this quantity in the denominator of our statistic over there, has to be greater than or equal to 0, so that HII has to be less than or equal to 1. So our diagonals of our hat matrix always have to be bounded from above by 1. This is a fact that we're going to use later on when we use our hat diagonals as a diagnostic measure. Okay, so let's just go through a coding exercise where we create standardized residuals and look at them.